Still open a bit. Okay, so good afternoon, everybody. Welcome to the third day of the COHESA Annual General Meeting. My name is Amir Abdelhadi, and I will be chairing this session. So each talk will be allowed around 17 minutes, including the Q&A session. We will start with Jonathan Liu. So Jonathan will be talking about anticipating and eliminating redundant computations in accelerated sparse training. This paper will appear in SK 222. Yeah, please, Jonathan.
Thank you. So while there has been a lot of work on accelerating sparse inference, in this talk, I'll be discussing our work on accelerating sparse training. So what I'm going to show you is that when trying to exploit sparsity in training, a form of non-zero redundant computation occurs that needs to be addressed, and I'll be describing our solution. So this log scale plot shows the flops versus days, or flops versus year. And what you can see is a 5 order of magnitude increase in training compute in less than 10 years. And so this has been driven by the desire for more capable AI systems, for example, AlphaGo 0 beating the world champion in Go. And this has happened by using deeper and larger neural networks that train for longer and with more data. And so our work is aimed at addressing this training compute demand. I'll focus this talk on convolutional neural network training, but there are details on how to extend the same technique to sparse matrix multiplications in the paper. So the computationally intensive part of convolutional neural network training is the convolution indicated by the asterisk, mainly to compute the weight gradient. So that's between the convolution between the activation gradient matrix and the activation. And the way this works is by sliding this matrix across the activation like so. And at each step doing multiply accumulates to produce each element of the output. So I'll give you this example here. So wherever there's overlap, we're doing multiplication. So that produces -2 and -6 plus a few zeros here. And we add that together to produce the final element in the output. Now you might have noticed a lot of zeros in the inputs, and that results in multiplication by 0. And so we chose to eliminate this multiplication by 0 by doing something called the other product. So that's the idea of taking all the non-zero parts of these elements, or of these matrices, and then multiplying them together like so. So this is also called the Cartesian product. And so we take these two vectors of non-zero elements, do every product between them, and that results in these products here. We can then map these outputs back to the output of the convolution. So the 2 and 3 appear right here. And then the -2 and -6 that we saw earlier, we can just pull those out, add them together to produce the -8. So now you might be wondering about these extra products here. You know, what are they good for? Well, it turns out that they're entirely useless. And so we call these redundant Cartesian products. And so this is the main problem that we're addressing with our work, and we'll be also discussing a solution to that. So our observation is that RCPs dominate during training, and I'll show you a bit of evidence of that. So during inference, the breakdown of computation such that most of it is zero computation with the type of sparsity that we're dealing with. So that's highlighted by gray. We can get rid of that with the other product, as I talked about. And that results in mostly useful computation. So that's the green part. Now in training, the situation is a little different. Again, we can get rid of the zero computation, but what's left is mostly redundant Cartesian products. So hugely inefficient and only a tiny little sliver of useful computation. So we designed the anticipator accelerator, to eliminate these RCPs. So we eliminate most of them, and that results in about 3.7x speed up and 4.4x less energy on average across a variety of deep neural networks that we tested on. So that was the executive summary. I'll now talk a bit more about the type of sparsity that we're dealing with, some characteristics of redundant Cartesian products, and then our anticipator accelerator, and finally the results that come out of that. So convolutional neural network training has 3 phases. The first phase is inference or forward pass. So that's a convolution between the weight matrix, which is a small matrix here, with a large activation matrix typically to produce an activation matrix for the next layer. In the backward pass, we do the weight gradient computation. That's the same computation that you saw in the earlier example. And so that's 2 large matrices that are convolved, producing a small weight gradient. And finally, there's the activation gradient computation. But in terms of matrix dimensions, it looks a lot like inference. So I'm not going to draw that again. So this is a lot of computation that has to happen. And so there's been some work looking from the algorithm side on how to reduce the amount of flops required, and in particular, how to introduce sparsity in the inputs while trading off a little bit of accuracy. And so what the sparsity looks like, as an example, is sparsity in both of the inputs. So both of the inputs can have the sparsity. And so our goal was to design hardware that can actually exploit the sparsity and get the speed up from not computing the zeros from the sparsity from both of the inputs. Another 2 characteristics of the sparsity is that it's dynamic. So it's changing from iteration to iteration. So you can't just cache the sparsity pattern and reuse it again and again. And secondly, it's unstructured. So there's no particular structure to where you can expect to see these zeros. And so that's another challenge in designing an accelerator. So that brings us back to the other product. With something like compressed sparse row, we can represent the sparse matrices as basically vectors of non-zero elements. And with these 2 vectors of non-zero elements, we just compute the outer product, and that results in eliminating all the zeros that exist in all the multiplications by 0 that would normally exist. And we can then create all the products that we need to produce the output. But that brings us back to this problem of redundant Cartesian products. So in particular, a question might be, why is it that redundant Cartesian products dominate during training? Well, the way to think about that is the amount of useful products, so that's these green products here, is related to the size of the output matrix. And the total amount of computation that happens in the other product is related to the size of the activation matrix. So effectively, we can compute what's called an outer product efficiency. So how efficient is the outer product at computing the output of the convolution just by dividing the size of the output matrix with the size of the activation matrix. So let's put some numbers to that. In inference, we have a very small a filter or weight matrix involved across a large activation matrix. So the output of that is just a slightly smaller activation matrix. And if we do the calculation, we get an outer product efficiency of about 97%. So certainly not a huge inefficiency, especially when compared to the weight gradient computation in the backward pass. So we have large matrices here, a large activation gradient matrix with an activation matrix producing a very small output. And if we do the calculation, that results in outer product efficiency of 0.07%. So that's saying that over 99% of all the multiplications that are happening in this outer product are completely useless. They don't contribute to the output. And so this is a huge inefficiency, and sort of leads us to the question of how can we detect whether a product is a redundant Cartesian product or not? So let's consider a single product. And it turns out we can figure out, say for a single product between an activation gradient matrix element and an activation matrix element, whether it's going to be an RCP or not. So let's see how this works. So in fact, this product is one of many products. So wherever there's overlap between the yellow and the blue matrix, we're going to do a multiplication. And for each element, it's going to have SR indices for the activation gradient element and XY indices for the activation matrix element. Now, if we take all the products wherever there's overlap and sum them together, by the definition of the convolution, that is actually a single element on the output matrix. And the index of that element is given by X minus S, Y minus R. So the relative indices between these two matrices. To give you a bit of context on how this relates to other product, if we take a subset of the multiplications here, we can map that back onto this overlapping product thing that's happening here. So these gaps that you see are because multiplication by zeros are skipped by the other product. So now back to this overlapping matrix multiplication. So it turns out that all these products here map to index 2, 1 on the output. And then if we slide this up, that would map to a different element. So in this case, 0, 0. Now the problem is that the other product computes these products over here. So even when we go too far up to the left or too far too far up or too far to the left, we're still computing all these products as part of the other product. And it turns out that this would map to -2, -1. So a completely invalid index on the output matrix. And the same thing happens in the opposite direction. So these are two cases where the outer product will compute all the products here highlighted in red, and they map to invalid parts of the output matrix. So this is where we get redundant Cartesian products. So the takeaway at this point is that just by computing the difference in the indices, so X minus S, Y minus R, we can figure out whether a particular product is an RCP or actually a useful product. Now we designed our anticipator accelerator pipeline to take advantage of this fact, but do this in a parallel fashion. So I'll give you a high level of how this pipeline works. So here we have these 6 stages of the pipeline, and each stage we're doing, computation or fetching from the SRAMs. So these green boxes are the SRAMs that contain the values and indices. And we've added this additional logic on top of an SKNN baseline. So this additional logic at stages 2 is going to look at the Y dimension of the output and try to filter out the inputs that would result in invalid outputs in the Y dimension. And then this third pipeline stage, we're going to look at the X dimension. It turns out this additional logic here is a tiny additional area overhead over SCNN. So all of this feeds inputs into the multiplier array. And so since we pre-filtered it, it's going to be more efficient in producing useful products. So now let's take a closer look at the multiplier 6 systolic array. So we used bfloat 16 in our evaluation, in particular 4x4. So what that means is that we have inputs coming in from the top and from the left. And then every cycle we're producing 16 products that we then have to map to produce the output. I'll give you an example using a 1x2 multiplier array, and let's see how this works. So from the example outer product from earlier, let's just grab the activation and activation gradient inputs, and then that produces 2 valid products. And so that's a good use of cycle 1. In cycle 2, we just swap out the activation gradient element, and then we produce this one valid output here. Now, cycle 3 is where things get interesting. So it turns out that these are both RCPs, but I'll just walk you through, internally, what is the anticipator pipeline able, thinking about and figuring out that these are RCPs. So for the 4, the output coordinate would be 2, 0. And so that's outside of the output matrix. And for the 6 here, that would map to output coordinate 3, 0. So that also lies outside of the output matrix. So both of these are RCPs. So in cycle 3, the anticipator pipeline will actually be computing these products here. So the -6, so the final valid product that we need. And so we're done in 3 cycles instead of 4 cycles. But let's scale this up and see how this works when we have lots of RCPs and larger multiplier arrays. So here's some 8 rows of computation, and the anticipator will be able to eliminate rows and rows of computation. So instead of 8 rows, it'll reduce that to a single cycle of 3 rows. And if you then scale that even further to entire convolutional neural nets and the entire training process, then we get results like this. So we tested across dense net ResNets and VGG and wide ResNets. And for most of them, we get over 4x speedup and over 4x energy reduction. So we get this dual benefit from both of these aspects of our evaluation. So in summary, sparse training calls for an outer product accelerator, which causes redundant Cartesian products. And so we designed an anticipator accelerator that eliminates 90% of the redundant Cartesian products, resulting in 3.7x speedup and 4.4x less energy overall. Thank you, and happy to take any questions that you guys may have.
Okay, any questions, anyone? So I may have a quick question. So in the speed up results, I've seen that VGG16 is basically is not giving a good results. Any reason for this from the structure VGG16?
Yeah, VGG16 has a lot of small layers, and because of that, it's much harder to eliminate the RCPs. And so you can see here that RCPs avoided is much lower than the other networks. And so that explains the results there.
Yeah, sounds good. Okay, now we will move to our next speaker. Deval Shah is here, right?
Yes, hi.
Hi. Yeah, so sharing is enabled. So Deval Shah will talk about label encoding for regression networks, please.
Yeah, can you hear me?
Yeah, I can hear you well.
Okay. Hi, so I'm Deval from University of British Columbia, and I'm going to talk about label encoding for regression networks, which was published in ICLR 2022 as a spotlight presentation. So regression has applications in several important fields, such as self-driving cars and autonomous robotics. In regression, a continuous value is predicted for a given input. A regression network can be trained by minimizing the squared error between the target and predicted values, which is called direct regression. However, we observe that up to 36% of accuracy gap exists between direct regression and task-specialized approaches. So though more accurate, such task-specialized approaches lack generality and cannot be used for any regression task. So the problem we focus on in this work is developing a generic framework for closing this gap. So in the rest of this talk, I'm going to talk about our solution, which we call binary encoded labels. So a regression problem can be solved with a set of binary classifiers. So in this case, the network predicts a binary code, which is then decoded to a real valued prediction. Since binary classification is a well-studied problem, it significantly reduces the design, implementation, and analysis efforts. Further, predicting multiple values instead of one also introduces ensemble diversity. So binary classification has been used by existing work on ordinal regression and multi-class classification as well. So this is a typical setup used by current approaches on regression by binary classification. In this particular example, each classifier identifies samples with label values greater than certain threshold. So this table represents the corresponding label encodings. For example, if the target label is in the range of 2 to 3, the target label encoding is 0001. Thus, each quantized label is converted to a binary target code using unary encoding. In this work, we generalize binary classifications used for regression by introducing encoding and decoding functions, expanding the design space of these label encodings. So now unary code is just one of several possible encodings with 4 bits and 3 values. So the design space of this label encodings explodes quickly with the number of bits and values. Practical regression problems have much higher numeric range, and thus they have much higher number of quantized label values. In fact, 10 to the power of 89 encodings are possible for a practical regression problem with 64 values and 8 bits. So finding a suitable encoding from this design space is crucial, as the worst code has 500% higher error than empirically found best code for regression benchmarks. But there has not been a systematic study on designing these codes. So now let's check a counterintuitive result where widely used error correcting Hadamard code proves to be less suitable for regression. So this is an 8-bit Hadamard code for 8 values. For example, this is the code for label 1 where all the bits are 1. This is the code for label 2 where alternating bits are 1 and 0. Here, each column represents the classifier's target for different label values. Hadamard code is well studied and has excellent error correction properties. So even if few bits are erroneous, the corrupted code can still be decoded to the actual value. Because of its error correction properties, it is used by existing work on multi-class classification, where each class is encoded using Hadamard code. And these encoded labels are used for training. However, we find that Hadamard codes are not that suitable for regression. So now let us take a look at our insights on why. So the first reason is classifier's error probability properties. So these are binary classifiers targets for different label values. So the classifier's target is 0 if the target label value is less than 64 or greater than 191. Thus, the classifier here learns a decision boundary for bit transitions between strings of zeros and ones. So wherever there is a transition from 0 to 1 and 1 to 0 in this range, the classifier has to learn a decision boundary for these transitions. Now it is known that the classifier is less accurate and it is more likely to make errors for samples that are closer to its decision boundary. Hence, in this particular case, the classifier has non-uniform error probability distribution for different label values, and it depends upon the placement of these bit transitions in the code. So the error probability of a classifier is much more higher for label values that are closer to bit transitions. Also, a classifier's bit decision boundary becomes more and more complex with more bit transitions, which also increases its overall classification error. This leads to an interesting trade-off between bit error probability and error correction capability when it comes to label encodings for regression. So let's compare Hadamard code with a simple unary code. Hamming distance is the number of bits changing between two codes. And it also gives a measure of how many bit errors can be tolerated. So more bit errors can be tolerated for codes with higher Hamming distance. For example, for these two codes, the Hamming distance between codes is 4 for header mart code. So even if one bit is erroneous for label 8, the corrupted code will still be decoded to 8 without confusing it with 7. However, for unary code, only the Hamming distance is only 1 between 7 and 8. So if this bit is erroneous for label 8, the corrupted code will be decoded as 7. So header mart code in general can tolerate more bit errors than unary code as it has higher Hamming distance between codes. However, some classifiers in header mart code has many bit transitions, which increases the complexity of decision boundaries to be learned by these classifiers. And it also increases the overall classification error. So header mart code has much higher classification error than unary code. Thus, even though header mart code can correct more bit errors, it also results in more number of bit errors for regression. Thus, a balance between these two factors is required. Second, for regression problems, the code should be designed to minimize the absolute error between decoded predictions and the target values. For example, for unary code, the Hamming distance between target codes for label 1 and 8 is much more higher than 1 and 3. So if the target label is 1, fewer bit transitions in this code will result in decoding the corrupted code as 3. However, more number of bit errors are required to decode the corrupted code as 8, since the Hamming distance is higher. Now, since the probability of making more number of bit errors is lower, the probability of making large regression error is also lower. Whereas header mart code does not show such kind of property. Here, the Hamming distance between codes for label 1 and 8 is same as 1 and 3. So the probability of making like regression error of 3 minus 1 is same as 8 minus 1, which doesn't help the objective of regression. Thus, the overall regression error for unary code is lower than header mart code since they are more suitable for the objective of regression. Lastly, we show that classifiers' non-uniform error probability distribution can be exploited to design more compact codes such as Johnson. Johnson codes are compact as it requires only half number of bits for the same number of label values as unary code. Now for Johnson code, the Hamming distance between label 1 and 8 is only 1. So for target label 1, if this particular bit is erroneous, then the code will be decoded as 8, resulting in large regression error. This suggests that this might not be suitable for regression because only one bit error is required for making this large regression error. However, as we showed earlier, that the classifier has non-uniform error probability distribution depending upon the placement of bit transitions. So here, this particular bit is very far from the bit transition. Hence, the probability that the classifier will make an error, this classifier will make an error for target label 1 is very low. Thus, the probability that label 1 will be confused at label 8 is also very low. Thus, the overall regression error is much lower for Johnson code. It also outperforms unary code for regression benchmarks. So this particular insight can be used to design more compact codes. Compact codes are desirable especially for regression problems with wide numeric range. For some of the problems like autonomous drivings, the numeric range of label is 700. This requires 700 quantization levels. So thus, compact codes are desirable as it reduces the number of classifiers required. We show that such compact codes outperforms unary code for several benchmarks. So based on these key 3 insights, we propose properties of suitable encoding, decoding, and loss functions that can be used for this setup of regression by binary classification. We also propose several suitable functions based on these proposed properties. We evaluate these sample functions on 11 benchmarks. that cover different network architectures, data sets, and 4 important regression tasks to demonstrate the generality of proposed approach. So for the evaluation, this particular figure compares different combinations of encoding, decoding, and loss functions for 3 benchmarks. Here, x-axis represents different combinations of loss and decoding functions, and different shapes represent different encoding functions. The y-axis represents the regression error, so the lower is better. So now the first observation from this plot is that there is huge difference in the error achieved by different combinations of encoding, decoding, and loss functions, since the variance of error, like the spread of error, is high. The second observation is that no single combination consistently results in the lowest error across different benchmarks. Here, the combination of unary code with D5 results in lower error, whereas here, the combination of hex J code with D2 results in the lowest error. So no single combination is the best. This shows that there is huge potential of systematically studying different aspects of this design space to design optimal encoding, decoding, and loss function for a given benchmark. We further compares BEL with generic regression approaches, such as direct regression and multi-class classification. We also compare BEL with task-specialized approaches. Overall, BEL achieves 10% lower error than direct regression. And it also results in 7.2% lower error than task-specialized approaches. BEL also beats state-of-the-art. It also achieves state-of-the-art accuracy for several benchmarks with significant reduction in the overall in the regression error. Thus, so in conclusion, in this work, we introduce a new design space of label encodings for regression, and we demonstrate the potential of this design space exploration by systematically studying the properties of suitable encodings. Our code is also available online. I would love to take any questions. Thank you.
Thanks, Deval. Any question? Anyone? Okay, so just a quick question, if I may. So, yeah, you use the Hadamard code. I have noticed that it has similarity to gray code. Did you examine also gray codes?
Yeah, we also
replication,
Yeah, so we also examined the gray code, and since the gray codes are designed such that only one bit changes between two two consecutive codes, they perform slightly better than Hadamard codes, but they are still not that great for regression because again, the gray codes are also have higher number of bit transitions across the across different codes. So they slightly outperform Hadamard code, but since though not significantly better than unary code or Johnson code, they results in higher regression error.
I see. Yeah, sounds good. Thanks, Deval. Okay,
you.
now to our next talk, Martin Weiss. We'll talk about neural attentive circuits. Martin.
Yes. Hi.
Hi.
Can you see my presentation?
Yeah, I can see. Yeah.
Okay, great. So yeah, I'm Martin Weiss, and I'm a PhD student with Chris Powell at Mila. And my talk today is going to be about our upcoming NeurIPS conference paper, which introduces a class of general purpose models with modular inductive biases that we call neural attentive circuits. So yeah, and if you have any questions, feel free to interrupt and I'll be happy to answer. So the broad research question of this work is the following: how can we make general purpose models more sample and computationally efficient? And neural attentive circuits seek to answer this question by taking a general purpose architecture that has the ability to ingest a wide range of input modalities and to add a modular inductive bias to reduce overfitting and sample complexity. This model makes the assumption that the underlying data generative process can be expressed as a system of sparsely interacting mechanisms. Now, I know there was a lot, so basically we're going to now take a step back, go through some background, introduce some of these key ideas, and then talk more about the specifics of how this model looks and what kinds of things you can expect from it. And then I'll conclude with a couple of the key takeaways. Yeah, so first off, like, what is a general purpose neural model, really? So for me, that is a neural network which can process arbitrary input data. And for a long time, we've had different neural models with baked in inductive biases for specific data modalities. For example, the convolutional neural network, which I'm sure most of us are familiar with, has some of these baked in inductive biases. A two-dimensional convolutional neural network has inductive biases that help it to process grid sample data like images. 1D conv nets are good at processing time series like the temporal convolutional networks. And convolutions provide inductive biases for locality and weight sharing, which kind of means that they're good for processing like pixels that are placed close together. That's kind of the locality, and weight sharing implies, searching for specific patterns that might appear anywhere in the image or in the sequence, in the signal that you're going to be processing. And more recently, we've kind of taken a step away from baking in that kind of inductive bias with the transformer. And so here I'm showing a vision transformer, which tends to need more data to perform well. But when you have access, yeah, Deval? No, okay. Yeah, but when you have a lot of data, it's kind of like a data sponge. So it can perform, outperform models with baked in inductive biases. But models like this, even though they can perform well on text data or image data or other kinds of data as well, they have a major drawback, which is that the number of attention weights scales quadratically with the input length. So what that means is that even if you have a giant model like GPT-3, you only have a context window of 2048 text tokens, or whichever tokens you like. And so obviously you can't read in like a whole book, or you couldn't read in a video. You're very quickly going to run into, or even if you want to do like prompt engineering, like you very quickly run into this this limitation. And that limitation is kind of because of scaled dot product attention, which is like the foundational component of the transformer model. And here, basically, the idea is that we have these queries, keys, and values, and the queries and keys are multiplied together, and it's basically comparing each query with all of the keys, and then using that to produce a value. And yeah, and that has this quadratic complexity. So yeah, on the left here, we have self-attention, which is like the key component of transformer models. Yeah, and it's clear here that it's self-attention, so the number of tokens in Q, K, and V are the same. And on the right-hand side, we have cross-attention, where the queries are coming from some other data source. Here I'm asking how many of the letters of the alphabet are contained in the keys and values being produced from this other example. And the cross-attention is between the queries are being compared to these keys, and it's extracting information from them based on this other input. So we have two sequences now, and they can be from different modalities. It doesn't have to both be text. It could be text and image or sound, or it could just be learned parameters of our model. And what that allows us is to decouple the dimensionality of the queries and the keys and the values. And that's important if we want to be able to process very large input sequences. So here I'm going to show you an example of what is a general purpose model in Perceiver IO. Here's kind of the read-in attention / encoding part. And yeah, so I'm just showing you the resampling cross attention, and that allows us to use a fixed number of query vectors, here termed the latent array, to cross-attend with a much larger number of input tokens in the input array. So that could be like 50,000 tokens as opposed to this 2048. And here I'm showing you the rest of the model. And basically in purple, we have this processing, which is a sequence of L modules. They're just doing self-attention, but they're doing self-attention across a number of vectors, which is not the same necessarily as the dimensionality of the input array. And then finally, at the end, you have this decoding step where you have this output query array, which is similarly just some number of query vectors that are being used to attend to the output of the backbone, this, those gray vectors there that have processed the input. And as a result of those, you get some output array that you can use for whichever task you like. And so, a key question here is like, how exactly are you formulating these, these different queries, because they seem really important for encoding inductive biases and doing all the processing. And the answer that DeepMind with their perceiver IO came up with is basically that for each different kind of task, like if you have masked language modeling, then you can just use the position in the sequence of the specific token that you're interested in. And yeah, you can have output specific features that produce outputs with different semantics as well. For settings where each output points to something that like is more complex, say like a multitask or multimodal setting, then we can use a different embedding for each one of these. And so you see that kind of on the right-hand side in the video queries. They have, an is video part of the positional encoding, which is used as the query. So I hope that gives a little bit of a background on the general purpose models. So now I'm going to answer briefly what exactly is a modular inductive bias, because we're merging general purpose models, modular inductive biases. And basically what this is that it helps a neural architecture learn a system's sparsely interacting neural modules. And systems like that tend to work really well in low data regimes. They're good at systematic generalization, like the neural module network, or with the neurosymbolic concept learner that relies on scene graphs. And they're good at like fast adaptation to new data, as long as those are coming from a certain class of distributions. So it has to be related to the original data. And the downside is that they're not very versatile. So that means that they can't really be deployed to new domains very quickly, and they kind of require like this specialized data set to train on. Like they'll have a scene graph, for example, that gets pulled in and used. And just as a reminder, the general purpose model is very agnostic to these input data types. It doesn't really have many domain-specific assumptions, and the downside of not having those inductive biases is that it can easily overfit and has a higher sample complexity because you have to kind of learn those inductive biases from the data. So that brings us to neural attentive circuits, the model which we're going to propose. So here's a very high-level overview of what that model looks like. So there's a couple key components here. The circuit generator on the top left outputs a circuit design, and that circuit design can it basically is used to condition the circuit executor. And the circuit executor takes in on the left some image, it can take in any other kind of input modality that you like, and then it processes it in some way and outputs some task-specific output. So like it could be a regression or a classification, etc. And yeah, the circuit design we can have a prior on this, on how the circuit design should look. So let's take a step in and talk about what that circuit design is. So what it's doing is it's deciding which modules in the circuit executor are going to talk to which other modules. And we do that by having each module be assigned a learned vector in some embedding space that we call a signature vector. And the closer the signatures of two modules are, the more strongly they're allowed to attentively interact with each other. And a circuit design also determines which module does what. So each module is assigned a learned vector called its code vector. And all the computation performed for this module is conditioned on this vector via weight modulation. And you can kind of think of the circuit executor as quite similar in some ways to perceiver IO, in that we have some cross-attention reading in data, which has been tokenized in some way. And then they're being processed by each of these different latents or modules through self-attention. The difference here, though, is that instead of like a quadratic self-attention that's happening, we do a different form of self-attention, which is sparse. So here we have just like the read-in attention, as I was mentioning, and the queries and codes. The queries are being conditioned on these codes that we're having output from the circuit design, as are the keys and values. And yeah, the propagation of information and processing of it is done in a sparse way using what we call stochastic kernel modulated dot product attention. So instead of just pure dot product attention, we are actually using a kernel to make this more sparse. And similarly, we have just another readout, which is very similar to the read-in, and but using these additional components that allow it to be in a learned space and be therefore sparse. So here's an architectural ablation. So we start like with the perceiver IO, then we add these modulated fully connected layers that incorporate the code for weight modulation. And we see, you know, a small improvement in performance. It's not anything major, and some performances even go down. When we add a sparse graph, so basically imposing that these modules live in a space and they're not all talking to one another, but it's not learnable, then we also don't get that much change in performance. It doesn't really work all that much better. It improves a little bit out of distribution though. And then finally, once we start encoding a learn, we incorporate a prior graph, and then we allow the model to learn on this prior graph, we see a jump in performance. So you kind of need all these pieces to work together. Yeah, and now I'm going to show you a couple other of the results of once you start incorporating sparsity, what happens. So here, the modular inductive biases improve few shot adaptation. Basically, we have these two few shot image classification tasks, and when you only provide one or two samples, we see that the neural attentive circuits outperform perceiver IO in a pretty significant way. And then that kind of goes away as you increase the number of shots. So in a really low shot setting, we perform better. We also perform better across a range of other modalities. So this is a ModelNet, basically a 3D point cloud classification task. And yeah, there's a huge benefit to using this kind of sparsity to basically have like a local receptive field, we think. Similarly, for list-ops symbolic processing, I'm not going to go into depth about these. You can see the paper for additional details, but basically it works much better for a range of different modalities. So this modular inductive bias seems to actually be something that's really useful for general purpose models, yeah, across a whole range of tasks. Here we're seeing the input is 4,000 bytes of IMDb text. So this is just raw. There's no there's no like byte pair encoding or anything, and the NAC is able to find these long-term dependencies better. And this is how it looks when you visualize the learned graph. And so here we have different prior graphs that we're using, and the model is learning these different kinds of relationships between the modules and constraining their communication pattern. And you can see that actually, if you zoom in a lot on these, there's actually this core structure that all of the models learn, which is like kind of this hemispherical setting. So you have like two kind of hemispheres on the outside. You can see them like right here. So that's like a hemisphere, and that's like a hemisphere. And then you have these little intermediate nodes which are communicating between them. You see that kind of motif appearing in all of these different graphs. And then when we sparsify, so we remove some of the model, some of the modules, we see like a big increase in the speed of the model, but we don't see that much of a reduction in the performance. So this is like an easy way for us to reduce the amount of compute used. So In conclusion, we have a few takeaways that general purpose models are out there and they're a good choice for certain multimodal settings, that sparse priors can be incorporated via the method that we proposed in NACS, and that those priors can improve computational efficiency, but also they can improve performance as well. Yeah, and so as I said, this paper is going to be at NeurIPS in 2022. Let's thank my co-authors, and I'm ready to take any questions that you might have. Thank you.
Okay, thanks, Martin. Any question from any of the audience? Okay, we will take a 5 minutes break before we continue. So we will continue at 2 p.m. sharp. Okay. See you soon, everyone. Thank you.
Thanks.
Hello, everyone. Let's continue. Our next speaker is Simon Baroy, and he will talk about improving meta-learning generalization with activation-based early stopping. Simon?
All right, thank you. I'm just going to share my screen there.
Sure.
Sorry. Okay. Wait. Okay. Do you see my screen?
Yeah, I can see it.
Okay. Just. Okay. Okay. Do you see the slides correctly?
Yeah.
All right. Okay, so thank you for inviting me. My name is Simon Giroy, and today I will present to you my paper titled Improving Meta-Learning Generalization with Activation-Based Early Stopping. It's a work with my collaborators, Professor Christopher Pal, Gonzalo Mordido, and Professor Sarah Chandar at Mila. And it was presented and accepted at the first conference on lifelong learning agents, COHESA 2022. So our problem setting is, in this paper, we study out of distribution generalization in the context of meta-learning. More specifically, our goal was to be able to understand OOD generalization such that we're able to infer how it evolves over the training time, with the practical aim that if we're able to do that, we can do a better early stopping to maximize generalization, the OOD generalization with respect to time. And it's a step forward to generally understanding OOD generalization and improving it in OOD settings. So, as I said, the practical goal here was to have principles and a method that allows us to do better early stopping, better OOD generalization. From this work, we gained a few important insights. First, we can say that in meta-learning, the out of distribution generalization to a novel task distribution, so let's say a novel few-shot image dataset, well, this generalization may be inferred from simple statistics on the neural activations of the network with respect to the target data, but using just a few unlabeled examples. And what we do specifically is that by detecting when the target and source activation trajectories, so trajectories of the activations with respect to the target and source data, when they start to diverge from each other, by detecting this time, we can better infer when the target generalization is reaching its maximum before it starts to degrade. And from these discovered principles, we propose the method of activation-based early stopping, or ABE in short. So, as I said, the problem in meta-learning, here we give the example of few-shot transfer learning for image classification, but in most OOD settings is that to infer generalization, we use a validation set, but itself is derived from basically the source data. And the problem is that depending on your downstream application, it may be pretty different from the data that you use to train your model, and you may end up with a significant distributional shift between the target and the source data. And what this can result is that depending on the shift, the optimal target early stopping time here in orange may be quite different than the stopping time you will get using the validation set. And if you stop using the validation set, this can lead to arbitrarily poor generalization. And what we want to do is to be able to infer how this orange curve evolves to stop at the optimum time to have as close to the best generalization we can get. So just shift this a bit. So basically, the core of our approach here, of our method, is to characterize how the model evolves as a function of its input by looking at how the distributions of the activations evolve over time. The intuition is that the feature extractor, I'm just going to give you an example here. By activations, we mean, okay, so given an input distribution, layers will have distributions over their activation vectors, and there is such distributions for each layer, and that's what we want to track. The intuition being that the feature in deep learning, the feature extractor is responsible for learning deep representations, and this comprises most of the neural architecture. So it makes sense that basically the feature extractor, the bulk of the network, is critical in determining the actual generalization. And to fully characterize how the feature extractor evolves as a function of its input, we need to track, we track how the distribution of activations at all layers evolve over time. And the idea is that since generalization is, but basically, I'm not going to be able to explain all the nooks and crannies, but the idea is that generalization will be tied to some function of the trajectory of the neural activations, such that there is a point in time where both coincide to the optimum accuracy. But how to find when to stop is we do this by actually comparing the trajectories of the neural activation distributions of the source and target data. The idea being that if on your downstream application, let's say optimum generalization is reached before maximum validation accuracy, well, you see that you will have a first time window where both accuracies increase, so they're positively correlated, and a second time window where one increases while the other one decreases, so they're negatively correlated. And that's exactly what you're going to try to find in the trajectories of the neural activations. A first time window where the trajectories go in a similar direction, and then another one where they start to diverge. But obviously, so our method can be broken down into three parts. First, we need a way to effectively and efficiently characterize the neural activation distributions to be able to plot in some space, like a point at each time, to basically end up with a trajectory. So we need a way to basically characterize where are those distributions going. And one way we can do this is using their moments. So just a little bit of a reminder, a random variable that admits a probability distribution under a certain condition, it's actually called Kalman's condition. Well, the probability distribution is entirely determined by the sequence of moments. As a reminder, first order moment is the mean, then the uncentered variance, et cetera, et cetera. And this is also true for multivariate random variables if Kalman's condition is fulfilled. So here you end up with high dimensional moments. The problem is, since so obviously for the source data, we have as much data as we want. It's it's sampled from the source distribution used for training. But for the target problem, in our method, we use just a handful of unlabeled examples. Basically, what we use is the support set unlabeled from a single target task, because we reason that this is the minimum amount of information that you can reasonably expect from the target distribution. But since you have so few examples, it doesn't make sense to try to estimate high order statistics. You won't try to estimate order 49 moment. So we need to do a cutoff to do a rough characterization of the distribution, and we cut off after the second order. So we only end up with first and second order moment estimates. However, you can see that there's still a lot of quantities to track in the high dimensional space, and you also want to further summarize those. You don't want a single feature to skew your analysis and saying, oh, well, according to this feature, the trajectories are separating, so we're going to stop there. So again, we're gonna summarize those moments, again using the idea of moments, but computed across feature dimensions. So before we do that, we can see that we have three discernible types of quantities. We have the elements of the mean vector, the diagonal elements of the autocorrelation matrix, and the non-diagonal elements. So to have a rich, I mean, it's a mix of what we like to call a theoretically sound way to generally characterize the distributions, but there's a bit of heuristic here. So here we decide, not entirely arbitrarily, but still kind of in a heuristic fashion to characterize those three types separately because they're discernible. So for the first type, the elements of the mean vector, we compute across feature dimensions the first and second order statistics. And for the other two types, we note here that since they're already of second order, we will just compute first order statistics. Otherwise, we end up with higher order and we have high estimation error. So we compute the first order moment of the diagonal elements of this matrix, and same thing for the non-diagonals. So there we have it. We have a compact four-dimensional space that gives you a pretty general way to characterize how the distributions are evolving. Of course, it's a rough characterization, but by linear combinations of those four dimensions, you can express actually many interesting metrics on the distributions. So basically what you do, given some input distribution, is that you compute using the samples you have, those four aggregated moments, and you do it at each layer of the feature extractor, and that's how you're able to characterize the trajectory of the activations of the model with respect to some input distribution. The next part of our method is that we need to actually find where in the network is the divergence happening, because our experiments show that, it is not enough to simply look at the final representations of the model. Sometimes, overfitting does occur, but if you look just at the final representations, you're not able to see it. But sometimes if you look under the hood at other deeper layers, you're able to observe that divergence, you stop at the right time, and then you actually improve the translation. So basically what we do here is simply look at each layer and look for, according to which hyperplane do we see two curves that have a strong negative Pearson correlation on a large time window, meaning that it shouldn't be negatively correlated for a short time, but for a consistently long period of time. And I just said that, you need to search across all layers because, depending on the setting, this critical layer may be at the last layer, at an intermediate layer, or the first layer. It depends. Just like which hyperplane in your space is going to be, you need to project those trajectories onto. Again, it depends on the application. One of the insight is that it's kind of pointless to try to find the golden metric that in all cases correlates with OD generalization. It's going to depend. What was the architecture? What was the source data? What was the target data? What was the way that you train your model? And so you need a general way to characterize how are those activations evolving over time. And same idea for on which layer you will be able to observe this discrepancy. So here, for example, it was observed at the first layer, which allowed us to stop at the right time. Here's just a little visualization where we see that when the two trajectories start to diverge, it actually corresponds to when the target accuracy, or in this case, the OD generalization, starts to decrease while validation accuracy keeps increasing. And finally, well, I've just explained it a bit earlier, but the algorithm, once it has spotted at which layer, according to which hyperplane there is a strong divergence, it will stop when this time interval begins. And it's based on the Pearson correlation, negative multiplied by the time interval. It's also important to note that this objective is defined in such a way that if the target problem is very similar to the source problem, and likely validation auto stopping was already performing well, Abe will stop at the same time. Because what we want is when there's no gains to make, when there's no generalization gains to make, we want to perform on par. We never want to perform worse than validation-based early stopping, but when there are gains to make, then we want to fill the generalization gap as much as possible. I'm going to be very quick here, but one of the reasons why we were very excited about this research is that we were able to show that these principle and this method works in a very large and challenging array of experiments. Basically, we use the meta dataset benchmark to constitute 48 pairs of source and target dataset, few-shot image dataset. For example, mini ImageNet to quick draw, from traffic sign to Omniglot, et cetera, et cetera. We also use 3 mainstream meta learning algorithms: MAML, prototypical network, and matching network. And we also did experiments with ConvNet and ResNet 18. And the results are that they're fairly consistent. I mean, very consistent, is that in general, when there's no gains to make, the method performs on par, which is what we want. And when there are gains to make, aka validation-based early stopping is not performing well, so there's room for improvement. Well, Abe is able to close a large portion of that generalization gap. And this is true across meta-learning algorithms, pairs of few-shot data set, and neural architectures. This is just a figure to show you that, so in each of those cases, the red line is the generalization gap of the validation-based early stopping. So meaning that if a point is on that line, it means that we're on par. As we can see, very seldom across those hundreds of experiments, there are points below. And the dotted line is the maximum performance you could get. This actually summarizes what I've just said. And the final experiments we made was that, okay, so since we use the data from a single target task to predict, to probe the neural reaction of the network, what if we use that support set of examples to actually evaluate the performance? And would that be a good metric to evaluate the generalization? And the answer is, well, it's way worse than Abe. So here, red color means performing worse than the validation baseline. Blue means performing better. So as you can see quite easily, there's a lot of red on that other baseline. And Abe, in this case, when there are gains to make, it does close the gap. So yeah, I think I'm pretty much done for the talk. I think the conclusions, the talk was pretty short, so you can remember well the conclusion. The idea is not try to find one golden metric to estimate how OOD generalization evolves, but rather have a general way to look at the activations of the network, be able to look under the hood, not just the final layer. And based on these principles, we're able to propose a method that performs very well in a large array of settings. So for this reason, we're quite excited, because conceptually, there's nothing that tells us that these principles shouldn't apply with other types of data. In principle, this might work whenever you have a deep neural net trained on something that needs to generalize to something else. So for our future work, we're in discussion with a lot of researchers to try to apply those principles to other OOD settings, such as continual learning, multitask learning, domain adaptation, other types of data, large, improving pre-training of large language models. And also another work will be expanding, those general principles to basically maximize OOD generalization with respect to not only training time, but other hyperparameters. If you'd like to read the paper or watch a short YouTube video, you can quickly screenshot the QR codes. And if you'd like to reach out for possible collaborations, feel free to email me. Thank you very much for your time.
Thanks, Simon. Thanks for the talk. So we don't have time for questions because we are 2 minutes over time. So if you have any question, please email Simon. His email is on the screen now. We will proceed to our next talk with Wael Alonaizi. Wael, are you here?
Yes, I am. Can you hear me?
Yeah. So Wael will talk about stealthy path planning against adversaries with non-deterministic behavior. Please, Wael.
I'm guessing you can see my slides. So I'm going to start. My name is Wael. I'm a PhD student in McGill University working with Clark Barberga. And our work is a bit different from you have seen from the past few days. Our paper got accepted in SIGGRAPH conference for motion in games. And by different, I mean it's mostly concerned with video games and the application of AI in video games. Now, when we talk about video games, one of the most common subgenres in video games is stealth games. And in that, players mainly focus on outsmarting enemies by actively avoiding their line of sight while taking them out from the shadows. Now, you know, this added constraint make it non-trivial for agents to be able to navigate in space. For example, if that task was given for an agent to navigate through space without being detected, it's not so trivial as if that constraint was not there. And our work is basically to create a method for improving the navigation for agents in these kind of scenarios. But you might be wondering, okay, what's the purpose of doing this in the first place? And the answer is, in some games, they introduce a companion, which is the player cannot be controlling, and the same constraints applying for that companion. For example, in the game of The Last of Us, they introduce a companion that were expected to be stealthy and moving around, but the thing is, the way they dealt with it in the game is basically they made them invisible, which of course breaks the immersion for players. And because if they didn't do otherwise, people or players would be frustrated because these agents or companions are easily detected. And in another application for this could be, for example, for providing some sort of a benchmark for assessing and assisting and designing game scenarios for stealth games. So a previous work explored how navigation can be happening using a RRT, which is a planning against scripted guards with motion. Now, most of the previous work investigated how, for example, the stealthy path planning would be against no observers, or when the observer's plans are known. So, for example, the agent has full information where the observer is going, which simplifies the problem. Or some of them even required human data to train on to kind of create a prior of how the agents would be moving in space. And of course, most of them did not really create a knowledge of the space. For example, they created a representation. Are you still, am I here? Yeah, you can hear me, right? Hello? Okay, good, sorry. So to understand the problem formation, first we represent the world from a top-down view where you can see the gray area is basically the walkable area. And an abstraction is just a polygon with holes inside of it. And we presented an agent, as you can see here in the black circle, and a goal target, which is that coin here. And we introduced, of course, the observers. The observers had a simple sensory capability, which is basically a limited field of view represented as a partial disk, this is the common way presented in video games. And they move through the space. Now, for what distinguishes our method mostly is we use a representation to kind of understand the space. And for this presentation, we chose to use the scale axis transform. And the feature of this graph is basically it simplifies the map into a planar graph that can go to any point in the map. And we kind of use this as a model to approximate the observer's motion on the map, on the level. Now we can look at the general pseudocode of our algorithm, and we can go in like really quick details of how it works. First of all, this algorithm works for every time step. So as long as the game is running, it's executing every time step. And for it modifies the roadmap we have seen. So how does it modify it? Basically, it kind of projects the location of these observers on the roadmap, and it kind of marks in a propagation manner where they can be going to next. So as you can see, for example, in this observer here, the area we have projected their location and we expanded their high likely positions, assuming that they're going to go moving forward. And they're not, of course, they're going to go backward, but it's since the algorithm is running every time step, we can adjust to that. The best way to see this is by looking like at this small video. As you can see that it's updated in real time, and you can see that the roadmap has been, it's colored by where they might be going next. All right. By the way, they are moving right now in a randomly. They choose a random point on the map and they just navigate to by the shortest path to that place. So you might be wondering, okay, what's the use of doing this? Well, basically, we thought of it in a sense that this could be what the red areas are no-go areas. They are not safe. So the agent can pathfind using this roadmap, which you can see in yellow, and find the path to their goal. So basically, we're trying to find a safe path. The next step will be to assign a numerical value to the agent's current position, which represents the risk for this agent. More on this will be, we're going to talk more about this later. And then next, simply, we try to find a path on the roadmap, bearing in mind that we've already removed the current observer's position. So as if we subtracted the edges from the roadmap. But as you can see here, our goal in the bottom right and the agent is at the top left, and there are no path. There's no path to take. There's no safe path to take. So what to do? Well, we used sub goals that an agent can navigate to in hopes that they will be closer to their goal. And it will maybe give them a strategic position. And the way we made them, these sub goals, we basically generated them around the corners in the environment. Now, this is a lot because there are so many points and it might affect the computation time. So what we did is that we, so here, this just shows you that we're going to get a subset of these hiding spots. Now, the way we get this subset of hiding spots is just by getting to the edges of the furthest we can go on a safe path. And then we take the subset of these sub goals or hiding spots. And once we have the subset of these hiding spots that we can go to as a sub goal, we assess them. By assessing them, I mean, we give them a value of how good they can be as our next sub goal. And for doing that, we basically calculated a weighted average for different properties assigned to each hiding spot. So these, for example, the occlusion utility, the cover utility, the proximity utility, they're all basically a measure of how well hidden this spot from the guards, from generally in the geometry of the space itself. And once we evaluate them, we take the best one and we mark it as our next goal, basically, or sub goal. And we find the shortest path to that goal. But of course, we have to evaluate, of course, if that path is safe or not. So if that spot is not reachable, then we remove that hiding spot and we consider the rest of the available remaining sub goals, subset of the sub goals. At the same time, at every time step, once we have a path that the agent is following, we constantly make sure that this path is safe, because as these observers moving, things will change because our plan might be obsolete. So this function here ensures that this our path will not be intersected by any of the observers. And if it's intersected, if there's a risk of intersection, then the plan is canceled and we go back all over again to find a new sub goal. So for our experiments, we run 400 rounds. Basically, the scenario makes up of the agent has a start position, the observers are allocated randomly on the map, and there's a goal position, and there's a time limit of 80 seconds. So the agent has to reach that goal in 80 seconds. If that agent reaches that goal, it's a success. If it doesn't reach that goal, then it's a failure. And we consider different parameters for these experiments we're running. I'm going to go over them right now. Of course, mainly the maps. We took inspiration from different commercial maps to have our data, our results to be more relevant. And of course, I mentioned before the observer's motion. We consider it to be a bit of more to the benchmark section where we wanted. We wanted the observer's motion to be random. So it kind of measures the highest risk, because usually games, they would have them in a scripted manner, which is relatively easier to overcome. But these two graphs shows us the performance of the observers of the brighter the area, the more it has been surveyed by observers. So they give a nice coverage for the a map using a simple random navigation through the map by picking just destinations and navigating to them. The observers, the default setting, we had 4 observers for each map. And to compare our performance with very simple benchmarks, first, of course, we considered our method. And second of all, we chose an agent that simply disregards any safety and goes straight to the goal. And the third behavior is another simple behavior where the agent has no motivation to move as long as they're safe. And basically, they just measure if they are the observers are close to them in their distance, and if they are too close, then they will just locate, disregarding any safety. So we checked the results, and here the orange or the red bars are based. So okay, so this represents the ratio of how often we achieve success in reaching the goal undetected. And the yellow is basically the simple agent who had no motivation to move, and it's kind of clear because they didn't do more than 20% in most maps. And the orange here is our method, which had a relatively nice performance. Bearing in mind that all these maps had 4 observers, so each map had the different properties that made it a bit difficult in some situations, and so on. There's more to talk, but I'll cut it short. We also looked into the possibility of modifying existing maps. For example, this is a map from the game Alien Isolation. And we investigated, for example, if we remove the dead ends, as you can see, there's a dead end here, we kind of connected them together, which we hypothesized that it might make it easier to achieve success. We also looked into one of the most famous games that came out recently, Among Us, and we also modified that map by adding more, removing more of the dead ends, sorry. And we look at how that affected their performance. So here we look at how the agents, even if they didn't reach the goal, if they achieved undetected, like if they at least achieve the second goal, which is to remain undetected, even if you don't reach the goal. So we can see that by removing the dead ends, the simpler methods had benefit more of this. But however, in our method also kind of improved the performance and had it more consistent through the maps. We also investigated how can we quantify, for example, changing the number of observers. How would that affect the difficulty or the success rate? So we've noticed that, okay, so for every observer we add in almost all of the maps, we've kind of reduced the success of this algorithm by 5%, which this kind of give a good indication, for example, of how can we categorize the difficulty for different settings for a certain level. Now, this is all nice, but what's the point of this if this algorithm is not really feasible in terms of running time? And we try to check out how this algorithm performed and comparing to the area of the map and the complexity of the roadmap, the graph we're using. So we found that in average, it's gonna give us around 13 milliseconds for every run, which is not bad, but it can be even further improved. And we also found out that regardless of the area of the map, the complexity wasn't more affected by the count of edges and nodes in the graph itself, because that's where most of the performance happening. For our future work, we of course want to compare this algorithm with how humans would behave using the same game. And in fact, we're doing that currently by running a user study to measure how people would perform against different types of observer patrol patterns. And we also looking forward to investigate how this behavior would be successful against different behavior. For example, scripted behavior, to motivated search behavior, where the observers are doing some sort of a heuristic search pattern. And of course, since this method had so many hyperparameters, we wanted to explore how can we improve the performance using machine learning or reinforcement learning to optimize the success ratio. Thank you so much for listening, and I'm more than happy to receive any questions. You're muted, Amir.
Yeah, thank you, Wael. Any questions from the audience?
Oh, and the source code is available, so I'm more than happy if you can just take a look and play around with the tool. There you go.
Okay, thanks, Wael, again. Yeah, if you have any question, you can email Wael. We'll proceed to our next speaker. Our next speaker is Doreen Chow.
Hello, hi, thank you,
Hi.
Amir. Thank you.
Hi. So Doreen will talk about the query processing and data quality issues on video analytics. Please, Doreen.
Okay, thank you. So today I'm gonna share one paper just accepted by ICDE next year, and its name is T-merge, track merging for effective video query processing. First, let's introduce some of background. Multi-object tracking, short by MOT, is a famous algorithm that to automatically identify the multiple objects in videos and representing them as a set of trajectories. It will assign a unique tracking ID for each trajectory, and it will find a sequence of bounding boxes for each of the trajectory and unique tracking IDs. But by our experiment, we found that most of the almost all of the tracking algorithm will face one issue that is called track fragmentation issue. Due to some reason, the ground truth, which you can see from this example, the green line, the ground truth track will be fragmented into two tracks, alpha and beta, because some reason like occurrence, because this guy in this walking on the street is occluded by another person for several frames, maybe 2 seconds, then the algorithm will consider as two different tracks and produce the track fragmentation issue. So why is it important? I'm doing research on the database, and we built several systems on answering the queries over videos. We're gonna use the results produced by CV algorithm as a metadata to answer the queries on videos, like involving the spatial or temporal information. Like TQVS will answer queries about the length of the object occurrences. So like answer queries with constraints with objects exist longer than 10 seconds. So the result of the MOT object tracking will matters, particularly for the longer tracks. The continuity of the longer tracks will matters for the subsequent outcome of the system, video querying system. So the objective, how we're gonna solve it? One iterative idea is that we find the fragmented tracks and then merge the fragmented tracks. Here we just shortly define some of the notations that we have a window, which is a video clip segment of the video, and the algorithm will find several tracks, A, B, C, etc. For each track, it is represented by a sequence of the bounding boxes, A1 to AN. That's all. And we can combine two tracks to make a track pair. And we denote all of the track pairs in this window by capital P. One iterative idea to find and merge the fragmented tracks will be that we calculate the distance between all of the track pairs. If the distance is lower than threshold, or we can find the top k lowest distance track pairs, and we can merge them, or we can doing some inspection on them to merge them. So the re-identification model, short as a re-ID model, will take input, take two images as input. So here the bounding boxes is actually part of the image. So we can take two bounding boxes as input for a re-identification model and output their distances. Actually, it will return two features of the input images, and we can calculate distance between two features. Okay. We can calculate the frame level distance by the re-ID model. That is dist A2, that's bounding box, and B3 a bounding box. That's the example. And for two track pairs, we can define the distance between two track pairs as DAB, which is the mean value of all of the bounding box pairs across the two tracks. Two tracks will have a bunch of bounding box pairs, like shown in this figure, and we just average all of the distances to use that representing the distance of the track pairs. So the approach will be iterative, that we just calculate the distances of all of the track pairs, and we can output the top k lowest distance pairs, which is be more likely to be the fragmented tracks. We did some experiments on several data sets and plot this figure. If we set k, we set k is a percentage. If we set k is like approximately 5%, which means we inspect 5% of the track pairs, top track pairs, the recall can reach 90%, means that 90% of the fragmented tracks can be found, which is fair enough. But this approach, the reality-based approach, will have a big problem. That is that because of the huge overhead to calculate the exact distance, we should extract the feature of every bounding box in the track pair, in the tracks and track pairs, and calculate all of the bounding box pairs in each of the track pairs. That's a huge overhead to do this calculation, and the huge overhead for the inference. So we propose an approach as a solution to this problem, which is the sampling-based approach named T-merge. Before that, let's look at the figure on the right hand. this is a histogram of the distances of all of the check pairs. Like here, we can say that on y-axis is a count, means this first rectangle means that only 2 check pairs with the distance lower than maybe 9, and so on. Maybe 3 is lower than 10.5. So you can see that in this window, only 4 check pairs are fragmented checks, need to be merged. So we just need to look at the first 2 rectangles, and all of the majority of the check pairs will be useless. So the idea will be that like we try to visit the check pairs with lower distances on the left hand, and try to avoid visiting the check pairs on the right hand, the majority of the check pairs. So we see visit. Visit means that from the beginning, we do nothing. One visit means that we extract 1 bounding box pair from 1 check pair randomly and calculate its distance. If we choose 1 check pair to visit, we just extract 1 bounding box pair from it and calculate distance. So the idea will be like visit the check pairs with lower distances as much as we can, and avoid visiting the check pairs with higher distances. Like I just said, visit the check pairs on the left hand, avoid visiting other check pairs. In other words, the idea will be to bias the visiting toward check pairs with lower distances. Following this idea, we propose our algorithm, which is T-merge. The procedure will be 5 steps, and the first 2 steps is initialization. We're going to visit each check pair a few times and maintain the average distance of the visited bounding boxes for each check pair. Means that we visit each check pair several times, and we know part of the bounding box pair distances. We just average them and denote as average D. And step 3, we're going to visit 1 check pair with lowest average D. After doing that, we got 1 new bounding box pair distance, right? And we're going to update the average D. That's steps 3 and 4. We're going to repeat doing step 3 and 4 several times, n times maybe. N is a parameter. That's a basic procedure. T-merge, we're going to have some improvement on that. But this procedure shows one thing, that is the first 2 steps, 1 and 2, is the exploration step. We're going to explore some of the check pairs. And the steps 3 and 4 will be the exploitation steps. We're going to exploit some of the check pairs which are more likely to be the target, that is the fragmented checks. Yeah. But this procedure has one big problem, that is easy to fall into the local optimum. Like if the exploration is not enough, means that for some of the check pairs, we just by chance visit some of the bounding box pair that close, but these 2 checks are not on the same person. That always happens. So we have one solution for that, is that we add uncertainty into that. This is one idea from the Thompson sampling. We just need to make some changes on the procedure. Still, we're going to visit each check pair a few times. That is our initialization steps. And step 2, we instead of maintaining the average distance of each check pair, for each check pair, we will maintain a beta distribution. And step 3, we're going to sample a check pair according to the beta distribution and visit it once. So this sample, a check pair, will have some uncertainty into it. for those track pairs are more likely to be a fragmented tracks, a target track pairs, the beta distribution will make it more likely to be sampled. But for other track pairs, still some chance to be sampled. The chance is lower than others, but still got some chance. So that's the uncertainty. And we're gonna update the beta distribution. For how to updating the beta distribution, I won't go into detail. You can check our paper. It's some math and some of the proof on that. But the basic idea is that we use the beta distribution and this uncertainty to make the track pairs with lower distance more likely to be sampled. But other track pairs are still a little bit lower probability, but still can be sampled. Still, we're going to repeat steps 3 and 4 several times. So here, yeah, n is a parameter. We're going to repeat it like it can be like 1,000 times or 10,000 times. That's a main contribution of this paper, T-merge. And we make other several improvements on this procedure. The first one is that we have a prior initialization of the beta distribution. We found that some of the track pairs have some property that make it more likely to be a fragmented track pairs. Like we get a property of their location or the property of their temporal location or spatial location. That's a prior information can be used to have to initialize the beta distribution. Without the prior initialization, the beta distribution will be all of the beta distribution of every track pair will be initialized as B11 maybe. But with prior initialization, it can be different. And second improvement is like we're gonna calculate upper and lower bounds of each track pair distance. If it meets some constraint, we'll just ignore them or pruning them to have the algorithm to be more efficient. And third one, we try to batch try to propose a algorithm to make it available for the GPU acceleration to batch this algorithm. Let's see some of the evaluation results of the algorithms compared. BL means the original real ID-based approach I just introduced, and we have other algorithms compared, like uniformly random sampling and another baseline multi-embedded approach. On the right hand, you can see that this triangle is the original baseline if we use real ID-based approach. And this blue curve is the randomly sampling. And our algorithm is a red curve. Sorry, it's a green curve. The figure on the top is that the algorithm without GPU accelerated, and the one is another one is with GPU accelerated. You can see that performance we're gonna be more than 100 times faster than the baseline approach, than the triangle, and around 10 times to 100 times faster than uniform sampling. That's all. That's the basic idea of our paper. Thank you. Any question, or you can email to. You can find my email on the screen. Any questions?
Hey, thanks, Darren. Quick question about the distance metric between pairs. How do you calculate it?
Distance of what? Of the check pair or the bounding box pair?
The check pairs. Like, what's the actual distance metric?
Do you mean this distance or this distance? The first one?
Yeah.
by doing this, we're gonna train the reality model. We retrain the reality model by instead of the original loss, we train the reality model by a triplet loss. By doing so, we're gonna have one property for the reality model that is first of all, reality model will get one image as input and output feature vector. That's what the reality model do. And we're gonna retrain it with triplet loss to make it have the property that if we input one image into it, get a feature vector, and input another image, get another feature vector. If the two images have the same person, the two feature vector will be Euclidean closure. We use triplet loss to ensure that. So we calculate the Euclidean distance between these two feature vectors.
Yeah, I see. So it's the Euclidean distance.
Yeah.
Okay, thank you, Doran. Any other question from the audience? Okay, so we will have a 5 minutes break before we proceed. So we will come back 3:03. Okay, so 5 minutes break. Thank you, everyone. Okay, everyone, let's continue. So our next speaker is Milos. Milos will be replacing Enrique. The talk is about a heuristic approach to memory footprint reduction in AI training, and it's called BitChop. Milos?
So Enrique actually presented BitChop already on Monday, so I'm actually presenting the Quantum Mantissa today.
Okay.
You hear me?
Yeah, sounds good.
Okay. All right. Hello, everyone. My name is Milos Nikolic. I'm a PhD candidate at UFT working with Andreas Moskowitz, and we work on accelerating neural networks. Today, I'm going to present Quantum Mantissa. This is our new method that abuses gradient descent to learn minimum Mantissa bit lengths for floating point training. All right, just a bit of motivation at the beginning. Neural networks are becoming ubiquitous. They're everywhere. They're pretty much outperforming classical algorithms in all tasks that they have been attempted. However, the problem is they're very expensive, especially training. So they're going to be both energy expensive and time expensive. And then our aim is to improve performance and energy efficiency of floating point training with simple changes to software and or hardware. So in this talk, I'm going to first cover a bit of background, that is how neural networks learn and why this is so expensive. Then I'm going to move on to how our approach to compressing floating points for training. And in particular, I'm going to talk about Quantum Mantissa that targets Mantissas only. And then we're going to cover results and conclusions. All right. So here we have just an overview of how neural networks learn. So we have a couple of layers on top. The first important concept that we have is the loss. And then the loss is going to be our proxy of how well the network is doing. So as our loss goes down, our accuracy and confidence of prediction is going to go up. And if we define loss this way, it is very simple to derive a way how we can update the parameters of the network to bring this down even lower. And that is, we find the partial derivative of the loss with respect to each weight or parameter, and then we bump this weight or parameter in the opposite direction. And if we do this for all of the inputs, so hundreds of millions or billions of times, we're going to slowly, step by step, decrease the loss, and that is going to increase our accuracy and then increase our confidence as well. The procedure itself is actually as follows. So we have two directions. First, we have the forward pass, and here we're going to stream inputs into the network, and then we're going to sequentially calculate the activations in each of the layers. So if we have this layer, we have incoming activations, we multiply them out by the weights, we are going to apply a differentiable nonlinear function that we call activation function, and then we have the input activations of our next layer. And we do this all the way to the end. And at the end, we get a prediction, and we can also calculate our loss. The second pass is backward pass, and here we have two steps. One is the weight update itself, which can happen here when we have incoming gradients from the next layer, and we just multiply them out by the activations, and we get our weight update. The way we get this incoming gradient is opposite of what we did in the forward pass. We start in the back, and then we propagate it slowly towards the front, and we do this so in comes the gradient multiplied by weights. It also gets multiplied out by the derivative of our activation function, and we have now gradients for our previous layer. And this goes all the way back. Now, in order to do this, every single step in our network needs to be differentiable. Now, the cost comes here because we have these activations that we've created in the forward pass, but we need to use them and consume them in the backward pass. And since they are, say, tens of gigabytes, that is a lot of data that cannot fit on chip. It has to go to off-chip memory. And since our operations with off-chip memory are 2 orders of magnitude more expensive than on-chip, this is basically the bulk of our energy costs right here. So stashing it and retrieving the activations. Now we are trying to reduce this workload by selecting a nice data type that's going to reduce the memory transfers we have. And most previous approaches boil down to something that I like to call select and pray. So you pick a data type, you train the network, you look at your accuracy at the end, and you decide whether it's good enough or not. If it's not good enough, you have to change the data type and then rerun training. And then most work here is going to concern with how can we squeeze out as much accuracy as possible from a pre-selected data type. Now, there is work on determining the data type. There is a lot of work that was done for inference. However, most of these are going to be very heavy-handed. They're going to have a lot of warheads, and they're not going to be applicable to training. We have two methods that were presented on Monday at the AGM that target the same goals as we do, and they do it in a very similar approach. So that's BitShop and ACGC. Now, our work now is quantum mantissa. So it's a lossy training approach that learns minimal mantissa lengths for floating point training. And very similar to BitShop and ACGC is going to target the loss. So if we remember from Monday, BitShop looks and observes the loss and then decides, depending on how loss is changing, whether we can remove a couple of bits or if we have to back off and then add a couple of bits. So such that the training remains on track, the loss continues dropping. Now, ACGC, on the other hand, cleverly sees that if we allow the loss to increase by a bit, we can analytically calculate how much this degradation loss is gonna produce slack in each of our tensors, so we can choose a data type for every tensor based on how much we are willing to give degradation for the loss. What quantum mantissa does, on the other hand, is it sees that the point of gradient descent is to reduce the loss. So if we add our footprint or our size of our data into the loss, it's naturally going to come down together with all of the parameters that are being learned. However, the problem here is that our footprint and our data type are actually not differentiable. And remember, we need the loss to be differentiable. And in order to fix this problem, we're going to have to redefine what the data means for us, such that it is differentiable. I'm going to make a couple of notes here before I move into the method itself. We are targeting floating point training. And the reason why we're doing this is because you still need floating points in order to get the best accuracy. Floating points are going to have three parts. So we have the sign, which we either use or we don't use, depending whether we have negative values or not. We have the exponents, which happen to be fairly easy to compress because here we have a distribution of the exponents, and you can see that they are very biased. So this can be losslessly compressed. And we have a method called Gecko that I'm going to mention later in the results, but is available in our paper that compresses the exponents losslessly. Now, what I'm going to concentrate on is the mantissas. And mantissas happen to be hard. And the reason is, again, in their distribution. They are fairly uniformly distributed. And then we have to have a lossy approach here. And we have to carefully choose what we're gonna remove, how much bits we're gonna remove. All right, so let's redefine our loss and data type. First, our new loss is going to be equal to the sum of the original loss right here, and this regularization term. So alpha i's are our new mantissa bit lengths, and they can be chosen per any group. In our case, we chose per layer and then weights and pressure separately because it works nicely. These lambdas here are just parameters that are allowing us to weigh this. These bit lengths, and we choose these such that they correspond to the size of the tensor represented by this alpha. So this is the proxy for our footprint. And then we also want this sum here to be equal to 1 for B-fold 16 for alpha equals 7. So it's normalized, and then we can use this gamma here just to choose how aggressive our regularizer is and how aggressively we're pushing down the bit lengths. Now we also need to define our data type. And we're going to start first with the integer version. So if we have n bits and n is an integer, we're simply going to keep the most significant bits of the mantissa. So n most significant bits. So in case we have n equals 3, we keep top 3 bits, and then we just discard the 4 least significant ones. And then in order to make this differentiable, we also need to expand it into the continuous domain, and we do this stochastically. So for a non-integer n, we find its two neighbors and the quantization values for those, and we select one of these randomly, where the probability is going to be the proportional to the distance of our non-integer bit length to its nearest neighbors. So say for a 3.3 bit mantissa, that is a 70% chance of getting a 3-bit mantissa, and then a 30% chance of getting a 4-bit mantissa. The way we save memory here is we use this quantization scheme in both the forward and the backward pass. So we actually only need to save these values here, but the 3-bit value is going to be part of the 4-bit value. So it's basically, we need to save the ceiling of our non-integer bit length. There is a bit of overhead in our method. However, it is just extra operations that are proportional to the number of elements in our tensors. So it's still going to be orders of magnitude less than the total number of operations we have for training. In our case, for ResNet 18, this was about 0.5%. So it's not really an issue here. All right, so let's look at some results. This is ResNet 18 on ImageNet, 90 epochs with gamma of 0.1. On the x-axis, we have epochs from 0 to 90. On the y-axis, we have number of mantissa bits. Reds are going to be our weights, blues are our activations, and the first thing I want to talk about is the spread on this graph. All of this right here. This spread represents the spread of the bit lengths from layer to layer. And then this justifies our decision to not go with one per network data type. So if we did that, we would have to do the worst case scenario. In that case, it will be about 4 mantissa bits, which is not really appealing. The dark lines here represent the weighted average. So you can see that instead of 4, we're doing about 1.5. Also, we can see that quantum mantissa works very fast. So we start with 7 bits. This is the default 16, and it drops by epoch 3, 4, or 5. We are already at 1.5, and then we stay here throughout training. What happens here at epoch 80 is we actually don't want to have a stochastic data type for inference. So once we deploy the network, we want it to be deterministic. So we round up all of our mantissa lengths, and then we keep them constant for the rest of training, just to let the network fall into its new bit lengths. Now, on this graph, we can see accuracy. Again, we have x-axis is 0 through 90 epochs. Y-axis is top 1 validation accuracy. Now red is going to be our baseline, and blue is going to be our quantum mantissa. And here we can see that quantum mantissa follows the baseline accuracy fairly closely. There is a bit of degradation here and here, but right here at epoch 80, we recover most of it. And remember, this is the point where we rounded up our bit lengths and are now running a purely deterministic data type. In the end, we have about 0.4% validation accuracy drop, if I remember correctly. All right. On this graph, I'm going to show roughly how quantum mantissa fits in together with Gecko into a full system. So this graph represents cumulative footprint that's normalized to FE32. So next axis we have FE32, we have bfloat 16, we have bit shop that was presented on Monday together with Gecko, and then we have quantum mantissa together with Gecko. Remember, Gecko was our exponent compression technique. And here we see that Gecko and quantum mantissa together reduce the footprint by 6 times in comparison to FE32 and about 3 times in comparison to bfloat 16. Furthermore, we can see that this dark blue right here, this is the activation mantissas in FE32, and this is the only part that quantum mantissa attacks, and it reduces it very substantially. It's by 92, almost 93%, and from a dominating contributor, it becomes a minor contributor in our footprint. Gecko, on the other hand, targets this light blue. This is the activation exponent. It also does a very good job. It compresses it by about 50%. Now, we've simulated quantum mantissa plus Gecko on ResNet 18 and MobileNet v3, and these are the numbers we got. So for performance, we got about 2.3 times improvement. And then for energy efficiency, we got about 4 to 6 times improvement. The reason why the energy efficiency is so much better than the performance is because we started with a memory-bound network. And Gecko and quantum mantissa work so well that we've switched our network from memory-bound, or most of the layers, from memory-bound to compute-bound. So we actually have a fairly limited amount where we can improve performance because we are hitting this hard bound that we can't go past. But if you remember from before, most of the energy costs come from our off-chip accesses. So our energy should scale linearly with our data type size, and we can see that here. Basically, what Gecko together with Quantum Matissa does is it changes the paradigm, because now we are compute bound and we can add cheap compute units that's going to take very little area, very little energy, and we're going to be able to improve our performance. All right, to conclude, I presented Quantum Matissa, which is our method that abuses gradient descent to learn a minimum Matissa lengths for FP training. It achieves similar accuracy to the baseline. It has a very significant footprint reduction. It is targeting training, but it also benefits inference, because remember, we learned a new data type and now we can use it for inference as well. As I mentioned before, Quantum Matissa works together with Gecko, but there's also BitShop. And all these three are included in the Schrodinger's floating point paper that is available on arXiv. That is my presentation. Thank you for listening, and I'll try to answer any questions that you have.
Thanks, Milos. Any questions from the audience? Okay, to proceed to our next talk, we are exactly on time. So thanks, Milos, again. Our next speaker is Nilofar Zarif, and the talk will be about using processing in memory for embedding lookups.
Hi, so can you hear me clearly?
Yeah, I do.
Okay, and can you see my screen now? Can you see my screen?
Yeah, now I can see it, yeah.
Okay. Okay, so hello everyone, I'm Nilofar Zarif from UBC, and today I will be talking about accelerating deep learning recommendation inference using processing in memory. Most of us are probably using recommender systems in our daily lives in different platforms like Facebook, Google Ads, or Netflix. Most of these recommender systems use deep learning to make recommendations. But the thing is that the deep learning models and the neural networks that they use are different from common types of neural networks like CNNs or RNNs that are used, for example, for computer vision. And the reason to that is that along with numerical features that all of neural networks have, recommender systems also have a large number of categorical features. What is a categorical feature? For example, let's take a look at the example of Netflix. A user at Netflix has a feature which represents the movies that the user has watched so far. This is a categorical feature because it includes a number of movies which are considered the categories, and it cannot be easily represented as a number. To be able to handle these types of features and use them in our neural networks, we use a type of layers called embedding layers. Each embedding layer includes a number of tables that we call embedding tables, and each table is storing the numerical representation of different categories of that feature. The operation that we do on embedding tables is called embedding lookup. And what is embedding lookup? Let's go back to the example of Netflix. For example, we have a user called Nilu. Nilu has watched Fight Club and Emily previously on Netflix. When we are doing inference for this user, during the embedding lookup operation, we use a hash function to identify which rows of the embedding table representing movies corresponds to Fight Club and Emily. For example, we find that row I and row J are corresponding to those movies. So we will fetch those rows, and at the next step, we will do an element-wise operation like sum or max or mean to get the final result of the embedding lookup. Embedding tables look something like this. They do have a number of rows, let's say n, which is equal to number of all the categories available for that feature. For example, in this example, it would be equal to all the movies that are available on Netflix. They also have a width, which is the number of columns of the table, which is, let's call it D. It's equal to some number that the ML engineers choose. It can be a power of 2, like 16, 32, or 64. Each categorical feature has its own table. And an embedding layer can have tens to hundreds of embedding tables. And each table can be like in order of tens of gigabytes. So this means that the total footprint, memory footprint of embedding layer can be in orders of terabytes of memory. So what's interesting about embedding layers during inference is the workload that they generate. So the workload that they generate exhibits very irregular memory accesses. It's almost random. So this means that the miss rate is very high, and instructions per cycle is very low. So we can see that memory is being kept idle for memory accesses. And the other thing is that they have very low computational intensity, because as we saw, they are doing just a very simple element-wise operation, like element-wise sum. So this means that a CPU is not being used at its highest capacity, and we are seeing low floating point operations per second. And the importance of these layers comes to light when we find out that at some data centers, like Meta's data centers, there are models being used that spend more than like about 80% of the execution time of each inference cycle in the embedding layer. So the solution that we are proposing to this problem is using processing in memory for embedding lookup to accelerate them. The processing in memory solution that we are using is a DRAM module that can perform computations right where the data lives. So we can avoid memory wall, and the limited memory bandwidth would not be a problem for us anymore. This approach has been tried by other researchers before. They have proposed a specialized hardware, and they have proposed their own design and simulated it and done experiments on it. But what makes us different from previous work is that we are using a real hardware for our experiments. And we are using the first commercially available PIM solution, which is a drop-in replacement for existing DRAM modules. This means that you can just buy one of these DRAM modules and place it in your current servers without having to make any modifications to the server. They are called UpMem DRAM modules, and they are delivered as a standard DDR4 2400D module. The architecture of the DIMM modules that we are using is something like this. Each DRAM rank has a number of processors that we call DPU, and DPU stands for Data Processing Unit. Each processor is an in-order multi-threaded processor with 24 hardware threads that we call tasklets. And each processor has access to instruction memory and also a working memory or a scratch pad, which are SRAM memories that are fast, so the processor can use while running our workload. And each processor has direct access to a 64 megabyte chunk of DRAM. And the thing is that processors cannot communicate with each other. So this means no inter-DPU communication. And each DPU is only able to access and read its own chunk of DRAM. But the good thing about this architecture is that we can achieve huge bandwidth potential. We can get up to 2 terabytes per second for 128 gigabytes DRAM, which is not like really large. So it's a very good bandwidth for that size. And like we can have 2048 DPUs on such a module. So considering the constraints and limitations that our hardware has, we have to design our solution such that it fits the hardware. One thing that I mentioned was that we have no inter-DPU communication. And we have addressed that when we are doing the pre-processing phase of our design. Our design has 2 phases: the pre-processing phase, which copies the data from the host memory to the DRAM module and places them on the DRAM DPU memories accordingly. And what we do to minimize inter-DPU connection is that we break embedding tables into columns. And based on the width of the tables, this means that we can fit, for example, if our table has 16 columns, we can fit 4 tables on one DRAM rank because each rank has 64 DPUs. Or if we have tables with 32 columns, we can fit 2 tables per rank. And each column will be copied to 1 DPU. And there's also one thing about our hardware, that the hardware is not capable of doing floating point operations. So during the pre-processing phase, one thing that we need to do is turning those values of embedding tables, which are floating points, into integers. And this is handled during the pre-processing phase. The next phase is receiving the lookup queries and redirecting them to the correct DPUs. So each DPU should receive only the parts of the query that is important to it. So we will look at what part of the tables and embedding data each DPU is storing and copy that part of query to the DPU. The DPU will process the lookups, and once the results are ready, we copy them back to our host processor and rearrange them and reformat them so they can be fed to the next layers of neural network and are ready to be used for the rest of the pipeline. And this is, again, where we turn those 32-bit integers to floating points, so nothing will change from the point of the view of the neural network. What each DPU sees in this architecture is something like this. It will see 2 arrays called the offsets array and the indices array, which are supposed to present a 2D array of lookup operations in a 1D manner. And each set of indices array represents 1 lookup operation. And this means that we will fetch the rows within that operation, do the element-wise sum with 1 hardware thread, and use other hardware threads for other lookup operations, and do this in a round-robin manner. And when the results are ready, they will be copied to a specific place that we have already allocated on the host memory, so they can be fed to the next layers of the network. So far, we have done some experiments, and we have seen that the characteristics of the workload that we are using, it plays a huge role in the speed up that we see from DPUs versus CPUs. For example, when we use a larger number of embedding tables, we can see the speed up change hugely. For example, when we increase a number of tables from 8 to just 14, we can see almost like more than a 30% decrease in latency of lookup operation. There are also some characteristics of the workload that we cannot be sure if are gonna give us a better speed up or not, like number of and the size of each embedding table. And this is something that we cannot be sure that how it will change the speed up, because it very depends on the access pattern of the workload. And there are some characteristics that we know, like when we increase that parameter, our speed up will decrease. For example, number of indices per batch. That means like the number of lookup operations that each GPU will handle per query. And when we increase that, the speed up will decrease, because each GPU has more work to do, and we are using the same number of GPUs while the work that each GPU is doing has increased. So combining all the different characteristics of the workload, we have so far seen GPU lookups being almost four times faster than CPU lookups. And we're still looking further into it and exploring our workloads and how our design works for them. So the conclusion, we saw that we can avoid memory wall and leverage parallelism available by PIM-DRAM module to reduce latency. And we saw that how the characteristics that leverage the parallelism that we have play a role in giving us better speed ups. We also saw that workloads with higher parallelism with higher speed ups. We also saw that PIM-DRAM accelerators can be used as a solution for recommender model inference workloads at data centers, because as I mentioned, we can just add these modules to current servers and use them for accelerating embedding layers. For future work, we are still looking into latency-bound throughput, because this is the main metric that data centers are interested in at large scale. So we would like to consider that instead of just latency. Also, we are gonna look into more real-world workloads and see how our solution is working out for those. So this was my presentation. Thank you for your attention, and feel free to ask if you have any questions.
Thanks, Nilofar. I have a quick question. So what's the, I have seen that you turn floating points into integers. So what's the impact of this? Like loss or, other impact?
Sorry, you were cut off for a moment. Can you please?
Yeah, I'm saying that I have noticed that you are turning floating points into integers.
Mm-hmm.
So what's the impact of this? Is there like any loss or other impact?
We have looked at the impact, and the impact was very little. So it was in the order of 10 by power of minus 13.
Mm-hmm.
So, and this is not anything considerable in the final accuracy of the network, because the impact is very small.
Right. Yeah, thank you.
Thanks.
Okay, thanks. Any other questions from the audience? Okay, thanks again, Nilofar. And now our next speaker is Puya Poland, and he will talk about memory conscious machine learning methods to extract time of flight data from flash lidars.
Hi, do you hear me clearly?
Yeah, I do.
Okay, let me share my screen and can you see my screen?
Yeah, I can see your slides. Yeah.
Great. Hello, everyone. My name is Puya. I'm a PhD candidate in ISL group under supervision of Professor Shankar Sane. Today, I'll talk about memory conscious machine learning method to extract time of flight data from flash lidars. This is a slight change of topic compared to previous talks we heard today. So I'll start my talk with brief motivation and why we're doing this, what are the applications, then I'll cover a brief background on these systems and the challenges of creating such systems and where we need improvements and what we're doing. I'll talk about the proposed architecture and we'll show you the Monte Carlo simulation result in comparison with the state of the art. LiDAR systems are basically widely used to measure depth and distance. In various applications, you can see some examples here, face or gesture recognitions, for example, or for security purposes, 3D scannings and modeling, which you might have seen in many modern phones or tablets like iPad Pro, for example. Autonomous driving is a hot topic today and is one of the main applications of LiDARs. My focus is mainly on the autonomous driving and 3D scanning for the applications of LiDARs. Let's cover some background and see how do these systems basically work. LiDAR is an abbreviation for light detection and ranging. Its concept is very similar to radar, but here instead of long waves, we use photons in visible or near infrared range of wavelengths to measure distance. Basically, the system sends some reference light. It would bounce back from the object and receiver will capture it. If we manage to measure this time difference between the light source and receiver side, knowing the speed of the light, we can basically measure the distance, which we call it time of flight because it's time of the flight of the photon. So how to measure this time difference or time of flight? There are two main approaches in measuring time of flight in LiDAR system: indirect time of flight or direct time of flight. In indirect time of flight, basically a modulated light source illuminates the object and sensors receive the reflections, and distance can be calculated by measuring the phase difference of the illuminated and received modulated light source. It has good precision in short ranges. The removing noise is typically easier because of the modulation, and hence it has a good SNR. But it's not suitable for long ranges because for long ranges we have to use a very long wavelength, and then measuring very small phase difference on long wavelength would be challenging. Direct time of flight, on the other hand, in direct time of flight, we use pulsed source. We basically illuminate target with a light pulse and receive the reflection, and we use time to digital converters to directly measure the time difference instead of relying on the phase difference. They have a high precision at long ranges because they no longer use modulations, but because we directly want to measure the time, the noise issue would be worse than the other one. However, we can use single photon avalanche diodes or SPADs for highly sensitive system. These diodes basically can sense every single photons. We can use them as our sensors to have a very sensitive system which is suitable for long range. It has lower SNR than in indirect time of flight, as I mentioned. However, and also in some implementation, it requires larger footprints. However, it is best for the long range application, and our focus would be on direct time of flight today. So how do these direct time of flight work? It's possible to implement LiDAR using basically digital front ends if we use single photon avalanche diodes. Single photon avalanche diodes are basically diodes which are biased with a voltage which is very higher than their breakdown voltage, and when they get light, it will trigger when they get one photon of the light, it can trigger an avalanche, and the avalanche will give us a pulse. So by converting these avalanche to pulses, we basically can count these photons. So one technique is time correlated single photon counting. You can see the simplified circuit here. By measuring the arrival time of these pulses with respect to the illumination, we know when we are sending the laser. By measuring the arrival time of these pulses, we can form a histogram then and calculate time of rise. So we basically send light many times, and then we form a histogram, and by looking at the histogram, we can see the peaks, which will show us the time of light, and knowing the speed of light, we can convert it to the distance. These systems are very scalable because they can be realized using mostly digital circuits. They have very high sensitivity because we are counting every single photon, but as you can imagine, the problem is the amount of data that is created, that is needed to count every single photon. So let's talk about challenges and the problems that we have. So yeah, as I mentioned, one problem is the amount of data. Imagine we have an array of SPADs, like a camera. We don't have single pixel, we want to have many pixels. Imagine if we have array of these sensor elements as SPADs, and they're being triggered by every single photon almost. A huge amount of parallel data is generated by them, and we have to timestamp each of the pulses that we receive and form a histogram somehow. That imposes a huge I/O bandwidth to the system if we want to transfer these timestamps off chip. Often we have limited pins, or we have limited power budget to transfer everything off chip. So there has been some on-chip histogramming designs. However, still on-chip full histogramming is impractical for large array of sensors. Imagine if we had 32 by 32 pixels, a camera with 32 by 32 pixels, and having 12-bit time to digital converter resolutions. We need the 32 by 32 multiplied by 2 to the power of 12 bins of that histogram, and imagine each bins is 8 bits. We require 133 megabits storage on chip to store this histogram. Then we also have to transfer this histogram off chip somehow if we want to get the image. For example, for 60 frames per second application, it would be something like 8 gigabits per second bandwidth requirement, which is very high for the systems. So some partial histogramming methods have been proposed. Basically, in these methods, the argument is that we don't need every part of the histogram. We can just keep a portion of the histogram. For example, this is an abstract of how TC-SPC system works. We can only keep this part that has been with the maximum count and discard the rest, right? By this, we can save memory and bandwidth that is required to transfer this off chip. However, this case have a challenge that this is not very easy to detect multiple targets. For example, in this toy example, we can see the red one are the targets very near, but the black one can be a target which is behind the main target. And if we just focus on the histogram with maximum bins, we just discard the other targets and we cannot detect it. Also, another challenge of this system is the background light, because the background light is also can equally trigger the sensors like our laser pulse. So we have to mitigate that as well. So let's talk about the proposed architecture. Let's discuss the proposed architecture. So we often use laser pulses for photon counting LiDAR systems. These lasers often have a Gaussian pulse shape, and that means temporal Gaussian response. They have a temporal Gaussian response. That means their reflection also have a Gaussian shape. on the other hand, the background light is constant because it doesn't have any correlation with the laser pulse. And then the histogram that we will see should have a shape of noise, the flat noise, and on top of it, some Gaussian peaks. So instead of creating a raw histogram or transferring data off chip, we can basically model the histogram on chip and just transfer the parameters of these models off chip. Gaussian mixture models is a simple and powerful method and works very well because, as I mentioned, our laser pulses are Gaussian often, and we can describe this basically using Gaussian mixture models. I can see high-level block diagram of our design on the right here. So in our design, silicon photomultipliers, which I mentioned, are a group of SPADs. So because these SPADs have a dead time associated to them when they're getting triggered by one photon, in order to not make the system blind to the rest of the photons, we can group these together to make one pixel. We can have one pixel made of, for example, here, 4 SPADs, and we call these silicon photomultipliers. So silicon photomultipliers with 4 SPADs are connected to TDC, time to digital converters. And then we have a per silicon photomultiplier cache to store timestamps coming from these TDCs, the TDC bank. We've considered 100 by 12 bits of storage because our TDC has 12-bit resolution. Then, after we store the timestamp from the TDC, after this cache is filled, the shared processing unit, which is shared across a group of silicon photomultipliers or pixels, these processing unit with GMM fitting and capability will perform expectation maximization algorithm to fit a Gaussian mixture model on the data that is stored in the cache. And we will repeat this many times, many cache fills until it will converge to the time of flights, basically, that we're interested in findings. These units have a scratch pad memory to store parameters required for calculations, such as responsibility value or gammas, and the mean, variance, and prior probabilities as well. Then we just, instead of sending all the data off chips for post-processing, we can only send these 3 out to reconstruct the histogram later, and we don't need to send all the time of flights or all the histograms. And also, so another ability of this system is that if we need more sensitivity, let's say we want to be able to work in conditions with higher background light, for example, direct daylight, or we want to measure distances in for longer ranges, like 100 meters. In these cases, maybe 4 SPADs are not enough because they're getting flooded by the photons from the background lights. So with these architecture, we can basically merge these silicon photomultipliers or pixels and kind of pixel binning approach. And by this method, their memory is also combined. So we can gather more data to fit GMMs on them. And that will make the system more suitable for long range or high background light conditions. Also, since we're using Gaussian mixture models, we don't discard information here. We don't discard information regarding the other targets. Imagine we're doing pixel binning, and since merged pixels are no larger, it's very possible that 2 objects would reflect light to the sensors. For example, we can in these micropixels, we might have one peak from the time of flight of the object 1, and then there's another object behind it. So there can be another pick. Since we're using Gaussian mixture model, if we fit the Gaussian well, we basically can detect both of them compared to other methods that are discarding the other ones all the time. So let's see some results and some test results. And first, the methodology, how we got the results of the system. We developed a custom designed Monte Carlo simulator that supports path tracings for simulating the system. This is a behavioral simulator. So the photon arrival times and the algorithm are statistically simulated here. The physical model event generator will get as an input laser and optics model, such as pulse length, wavelength, aperture of the receiver lens, and target models such as the reflectivity, its distance, and a model of background like the solar radiation, or in case we have indoor lighting conditions. And then it produced some raw events, basically a list of photons that probably will hit the sensor. Then according to pixel structure, we can filter these out. Basically, we miss someone because of the dead time of the SPADs, or how many of these sensors we have in pixels will affect how many events we can detect totally. Then these valid events have to be time stamped by the TDCs. So the TDC models also is fed to these simulator using the TDC space, that some like its sampling rate, the resolution of the TDC. And then the output would be time stamp, which then we apply our algorithm, which here is expectation maximization on it, and basically do all sort of on-chip, simulate all sort of on-chip processing here. A version of this simulator is available on GitHub. You can take a look and see how it works. Here you can see the reconstruction example overlaid on the histogram for one case that the target is at 18 meter, and there's a secondary target behind it at 22 meter. You can see it's basically we could reconstruct it with good accuracy and get two peaks very clearly. And you can on the bottom plot, you can see the convergence of mean and variance of the Gaussian mixture model kernels. And this in this simulation, we used Gaussian mixture models with 4 kernels. So you can see 4 lines which show the convergence of each kernel. You can see the green and red ones have converged to the target fairly quickly, under about 20 iteration. The very light red dashed lines show the golden targets that we have to see, and you can see the convergence of the variance. As we know, the laser is very short, in order of nanoseconds, so it has a variance, has a very low variance value. You can see they converged to that fairly quickly. But a question is that how to figure out which kernels have basically converged, or how confident that we are about the result we're getting from the model. So we wrote a confidence metric as prior probability of the GMM over the variance of each kernel, because we know the variance should be a low value. So if the variance should converge to a low value, and because we should get most of our reflections from the laser reflections, the prior probability for the kernels that are for our time of flight should be high. So higher probability, lower variance means that we're more confident that we found our target, we could model our target. In this plot, you can see the distance versus measurement error sweep for flash LiDAR mode. The flash LiDAR means we have multiple pixels that are working simultaneously together. In flash LiDAR mode, you can see that if there are distinct peaks on the histogram and enough samples are collected, the error is basically minimal. It's not necessarily increased with distance because we will converge to those peaks anyway. And you can see up to 16 meter, the error actually is decreasing, and it has a couple of reasons. One is if the laser is powerful enough so that we have a clear reflection of the target, which is in our case, we use 100-watt peak power laser. In this case, if we go further from the laser up to some distance, the effect of after pulsing is less dominant because less power will reach to the laser surface, and it will make, I can say, it will make the sensors less unstable. Also, the pileup phenomenon due to the powerful laser is diminished as we move away from the distance. Although this is true for up to some distance. After that, when we move, because the reflection power will be close to noise level, our error would be higher as well. Here on the bottom, you can see the confidence metric for the detections. As you can see, we are always between 60 to 80% confidence for the main target, and the red one shows how confident are we to detect the secondary target. And this is normalized, the confidence metric is normalized for each kernel. These ripples that you can see here are due to the fact that we are sharing time to digital converters for 5 pixels simultaneously. As I mentioned, this is the flash or multi-pixel mode. So how it performs compared to other techniques, we also simulated the results taken from the other compression techniques that is used in LiDAR systems. For example, partial histogram, as I mentioned, it zooms over the bins with maximum value until it reaches a very high res and precise number. However, doing this, the secondary target is completely lost, and the system has zoomed over this one. Also, in noisy environment, we might not zoom on the actual bin. For example, in one step, if noise causes one of our bins to have a higher value, we will zoom over that and we cannot recover, basically. There are centroid or averaging methods, basically serially average the time of flights over time. In these methods, they are very simple. They compress the data into one single value because they basically calculate the average of the time of flights coming from the TDCs. But the problem is that the secondary target is lost. For example, here you can see the convergence of a centroid method. The secondary target either is completely lost, or if it's strong enough, it can basically make a deviation into the centroid, makes the centroid not exactly a time of flight. However, you can see in this work, expectation maximization, you can see that for a similar situation, you can see we can detect multiple targets fairly quickly in under 10 iteration, while we're still keeping the IO bandwidth very low. You can see also the comparison chart with other works. This work uses flash lidars. Pixel binning allows for long range measurement. Basically, in our system, we can merge every pixel that we have together to work as a point mode, and in this case, we can measure up to 100 meter. And we only need to transfer 64 bits per pixel because we have 4 kernels, and for each kernel we have to transfer mean value and variance value and prior probability values, which totals to 64 bits, compared to partial histogramings that are 900 bits required. For example, in design 3, 900 bits are required to be transferred out to read the histogram. And since we're simulation, I have not calculated the bandwidth requirement, but assuming, because the bandwidth would require simulating the circuit and considering the circuit limitation, but assuming we're not computation limited and have a budget, IO bandwidth budget equal to this 1 to 3, this design can reach to 250 frames per second compared to 30 frames per second of the other ones.
Sorry to interrupt you, or over time, so if you can.
Yeah, I'm done. So here the reference is the comparison that I made, some state of the arts. And yeah, thank you. If you have any questions, I'll happy to answer.
Thank you, William, for the talk. One quick question. So how much reduction you achieve in external memory bandwidth and storage?
So in external memory bandwidth, as I mentioned, this is an architecture and we haven't yet created a full circuit. So we have to consider the circuit limitation as well. But the comparison would be, for example, we only need to transfer 64 bits per pixel in this design, while other state-of-the-art designs require much more, like 900 bits per pixel for partial histogram. This one has lower bits per pixel, but this one just uses the average and is not as precise as our other methods. So you can see in terms of more than 10 times savings in terms of bandwidth is potentially achievable.
Okay, and another question. By pixel binning, you mean it's the averaging of like a group of pixels?
So pixel binning, I mean, we can group the pixels and consider all of their detections as one pixel.
By averaging?
By collecting all of the samples into their caches and then considering all of the caches together and fit the GMM on all of the pixels, not on one of them.
I see. Okay, sounds good. Thanks. Any other questions from the audience? Okay, I think we're good. So we end with this. And thanks everyone for attending. Thanks for our speakers for the talks that you gave today. And have a good evening. Thanks everyone.
Thanks. Bye-bye.